They're both kind of short. That's good because that sets us, oh, I know I was going to show you guys. Check this out. Because I was like, oh my gosh, there's not much left. Let's see, you guys are right here. Oops. There's like only 2 parts left. And I'm like, what the heck? I'm not going to have enough time, or I'm going to have too much time. But here's the deal. I added a column. This column that says slides is how many slides there are. Okay, so today we're going to do our 8 slides and 15 slides. Because you count slides, so do I. Okay, but check out our last 2. 41 slides. Now, part of them are just screenshots of like maybe Ka values or Kb values, I'm not sure. So 41 slides and 63 slides. I'm just telling you, it's a little lopsided. Okay? I'm just kind of, and good, bad, otherwise, the reality is, you figure with part 8, we're going to be bumping up against your unit exam. So I'll try to kind of tell you what, well, I don't know, we'll see. Assuming I don't have to be gone for anything, maybe we'll have a breather day in there. We'll see. I hope so. That would be nice, wouldn't it? Because your test is, you guys have a lab, another lab where you use the pH meters on Thursday, and then the following Thursday you have your unit exam. So that's kind of. All right, so let's knock out 5 and 6 today. Part 5 might feel kind of familiar because it's definitely got some similarities to part 4. All right. Okay, so instead of dealing with weak acids, we're going to deal with weak bases and kind of do a similar thing. So one of the things, and we'll be talking more about this, but I'm hoping that if somebody threw at you CH3COO with a -1 charge, actually that's the acetate ion, you'd be like, ah, proton donor, proton acceptor. I'm thinking proton acceptor, okay? So in that case, acetate works as a weak base, proton acceptor. Kb also gives it away. The fact that I have a Kb value up here next to that species, CH3COO -1, I bet it's a weak base. So in this problem, we're supposed to come up with the hydroxide ion concentration and the pH. So hopefully your wheels are moving. You're like, oh, if I can get the hydroxide ion concentration, then I can get the hydrogen ion concentration, H+, and from the H+, I can get the pH. Or else you can go from the hydroxide to the POH, and from the POH to the pH. So right off the bat, you need to be able to do this. And this actually is one of the skills that you guys are working on, I think in part 1 and part 2, where you show it being a proton acceptor, as weak bases do. What's it going to accept a proton from? An H+ from? A water molecule. When it accepts an H+, what's it going to look like? It's going to look like this over here, CH3COOH. That H+ brought a positive charge. It was +1, it was -1, now it's neutral. The water molecule, it kicked off a proton. If you take H2O and take an H+ from it, you're going to get OH-. So be able to write that. The next thing is be able to write the Kb expression. So, of course, our Kb expression, it's products over reactants raised to stoichiometric coefficients. So this is your equilibrium constant expression. Kb is equal to molar concentration. This right here, I'll go ahead and write underneath it, because this is kind of a common sort of species to deal with in problems. I call this acetate, right? This guy over here is acetic acid. So I'm going to put WB, weak base, and actually I'm going to put WA over here, weak acid. The beauty of, or the reality, the chaos associated with chemical equilibrium. So yeah, so on the product side, we put the acetic acid, CH3COOH. We also put the molar concentration hydroxide ion, both raised to first power. And in the denominator, we put the acetate, CH3COO. -1 is equal to the Kb, which was given in the problem. Cool. Well, kind of like I did before, and actually we're going to end up with an ice table. In the problem, it said that this was 0.10 molar, right? But we can't, it's not a simple one-way arrow. If it were that simple, we could just go over here and put 0.10 molar, 0.10 molar, but we can't do that. Because it doesn't entirely ionize. It goes back and forth. This right here, by the way, is what we call the initial molar concentration, or CH3COO, CH3COO minus the initial concentration. Okay, so here's our ice table. If we let the X be equal to the amount of CH3COO minus acetate ion that what we said hydrolyzes or attacks that water molecule, okay, then it looks like this. Okay, so initially, again, it's like we talked about the other day. Is it true to say that pure water has 0 hydroxide ion? No, because it normally will give you 1 times 10 to minus 7th molar, but it's pretty much 0 compared to what we're going to be seeing going on. So we have a negative X, a plus X, and a plus X. And then at equilibrium, we know that we take your initial and apply the change. So at equilibrium, for the weak base, it's 0.10 minus X. For the hydroxide ion, which is what we're after here, to get hydroxide ion, and then on to our pH from there, X, and then X also for the CH3COOH, acetic acid. All right. And I don't know if you remember, but we have that simplifying assumption. But before the simplifying assumption, this is what it looks like. So we have in the numerator an X and an X representing your acetic acid and your hydroxide ion. In the denominator, the quantity we have is that 0.10 minus X, which is your acetate ion at equilibrium. So the simplifying assumption we've used before is to assume that X is pretty small. Pretty small compared to what? So X is double less than 0.10 molar, which was what we started out with as the molar concentration of our base, our weak base. And if that's the case, if that's really wimpy, then our 0.10 takes over here. So then this quantity, 0.10 minus X, is the same thing as 0.10. And it makes your life, my life, a little easier. So now apply the simplifying assumption, and we have, oh, by the way, and this is what I glitched on Wednesday, greater than, less than. It's the same rule of thumb as our weak acid. This works if you take 100 times your Kb, so let's check this out. 100 times 5.6 times 10 to the minus 10th is what? 5.6 times 10 to the minus 8th. 100 times that. Is that indeed less than the initial concentration of our weak base, which is 0.10? And I'd say yes. Okay, so you're in good shape. Like I said, I apologize. I switched that up a little bit on Wednesday. So after our simplifying assumption is applied, then the denominator becomes 0.10 instead of 0.10 minus X. And now we can, I usually cross multiply and then take the square root of. So we're going to take the square root of 5.6 times 10 to the minus 11, which is 7.5 times 10 to the minus 6. And by definition, according to our ICE table, that is the molar concentration of the hydroxide ion. ICE tables, I think they're nice too. They help kind of stay organized. My husband Carl just the other day was saying, I like those ICE tables. By the way, on this Thursday, I think he's going to come make a road trip and kind of, so you can put a face with a name in case you're interested in signing up for organic chemistry. So we'll be good for that. Okay, so the follow-up question was, what is the pH? I don't know how to do this. Oh, by the way, a little postscript here. If we were to use the quadratic equation without applying the simplifying assumption, it looks like we would still get the same value for x. So that's always nice. All right. So off to find our pH. So one way to do it would be this. We remember that for any solution, dilute aqueous solution, your hydrogen ion times your hydroxide ion, if it's at 25 degrees Celsius, and remember this is where we had that little discussion. This could be 1.008 or 1.01 or 1.0. Anyway, rearranging that, solving for the hydrogen ion, we get this. So the hydrogen ion is equal to that's a kW, right? The kW divided by the hydroxide ion concentration at 25 degrees Celsius. Okay, so substituting in then your hydrogen ion concentration will be 1.0 times 10 minus 14 divided by your hydroxide ion concentration, 7.5 times 10 to the minus 6th. Rounding to 2 sig figs, you're looking at 1.3 times 10 minus 9 moles per liter. So then, of course, to get to pH, we're going to take the negative log of that. So taking the pH is equal to the negative log of 1.3 times 10 minus 9. Again, we have 2 sig figs in the molarity. To show 2 sig figs in the pH, we're going to show 2 decimal places. So you should get 8.87 is the pH. And it never hurts in all chemistry problems and all physical science problems to say, now does that seem reasonable? Yeah, you were thinking it'd be basic. Okay, not crazy basic. Okay, that's on the other side of 7. All right. We'll do short. No. So the solutions are already there for this part, but not for part 6. Part 6 is interesting to me because this is the first semester I'm using OpenStax. And when when we redid our PowerPoint slides, this is a topic that actually we covered in past semesters. We covered the subject like way earlier. So let's see what you think. Conjugate acid-base pairs. And you've already seen them before. If you look on either side of the reaction arrow or either side of the equilibrium arrows, and if you can find 2 species that differ by a proton, then you have identified an acid and a base pair. Acid-base conjugate pairs. Conjugate acid-base pairs. Okay. For instance, remember one way we said to this HB looks like a weak acid, a proton donor. Remember the B doesn't mean boron, it just means something else. It kicks off its proton, you can kind of see the top way arrow, and it gives us the B minus. It accepts a proton, and it turns the B minus, accepts the proton, and turns back into HB. Okay, that's it all day. Dynamic chemical equilibrium. So those two, and you're going to hear me call them different things, they differ by a proton, and they are an acid-base pair, specifically a conjugate acid-base pair. Which one's the acid, which one's the base? I don't know, I have to look at it, see which one's got the proton, which one doesn't have the proton. Okay. So notice which is which, right? Well, if we call from left to right this the acid, then it's yin and yang. It's yang over here is the conjugate base. Well, what if we're going from right back to left again? We would call that the base, and this would be its conjugate acid. So, I don't know. Conjugate acid base pair covers it all, whether we go from left to right and right to left again. So here's some more examples. See how you can see how they differ by a proton. Looks right. Differ by a proton. And again, I mean, what's the acid or base? Which one gets the word conjugate? I don't know. I don't care. Conjugate acid-base pairs. Okay. So I guess I do care because these are kind of written from left to right. They're always also going from right back to left again. So from left to right, what is the? Oh, you already have it, don't you? The H3O plus, the hydronium ion, cation is being the proton donor. And the H2O is being the proton acceptor. So acid and its conjugate base. We did a problem with sulfuric acid Wednesday. And I don't remember what we did on Wednesday. And we said actually it's, I'm not real thrilled about this example because it looks like sulfuric acid is one of your 6 strong acids. I'm a little troubled by this because I would think it's a one-way ticket to kick off its first proton. But I guess I'll go with it. This is clearly acting as an acid donor, so it's the acid, and that would be if you its conjugate base, a different proton. More examples. Nitric acid, again, one of your 6 strong acids. I think this should be a one-way arrow. That's just me. This seems like a one-way arrow. So does this guy. Seems like a one-way arrow. Okay, HNO3 is clearly your acid, so NO3 negative, the nitrate ion would be the conjugate base of the nitric acid. Now this is a weak acid. Ammonia, NH3 can ammonium cation can kick off a proton and give you the ammonia. So make sure we're all on the same page here. This drives me nuts too. So this is ammonium cation. And this is ammonia. Okay. So ammonium is acting as the proton donor, an acid, and its conjugate base differs by a proton is ammonia. HCl is another strong acid. But in the context of having different by a proton and conjugate acid-base pairs, the HCl is the acid and the chloride ion is its conjugate base. Okay. So here's the deal. We talked about how weak acids have Kas, they're ionization constants, and the Kb is an ionization constant for a weak base. Well, if you look up, and I'm going to show you in a minute, a little bit, a table that we looked at before, if you find the conjugate acid-base pairs, you look up the Ka for the acid, the Kb for the base, you multiply them together, and you're going to get Kw. I'll kind of show you why that is a little bit. We said that in just regular water that doesn't have anything in it, it's going to do this. It's going to break apart and give you equal molar concentrations of H plus and OH minus. It doesn't do it to a very big extent. The Kw is 1.00 times 10 to the minus 14, or 1.0 times 10 minus 14, which, like we used earlier. If you take the square root of that number, that's where we got the molar concentration of the hydrogen ion and the hydroxide ion. H plus and the OH minus is equal to 1 times 10 minus 7. Anyway, so we kind of have that going on. Now let's take a look. This is I'm trying to remember, I think this is a proof. I'm just going to show you I'm basically going to show you why this is. All right? So here we go. Let's consider a weak acid. I'm going to put Wa up here, because that's kind of our generic weak acid we've been talking about. We can write a Ka expression and it would look like this. Well, let's kind of stick with that idea and let's consider the weak base. Now, can you see where the weak acid and the weak base have the relationship I've just been talking about? They differ by a proton. So ta-da, they are the conjugate of each other. And I could write my Kb expression like this. Well, let's say I take these two, I draw a line, and I add them together. See anything that can cancel? My HBs, my B minuses. So what do I have left? I have the auto-ionization of water. And what did we say with chemical equilibria? What am I going to do with my K's? I'm going to multiply them together, exactly. I don't have it here, but can you see where if I take this quantity times this quantity, multiply them together, do you see anything else that will drop out? The same ones, yep.
Does it always work that way for like the equations?
Yep.
Whatever cancels in the equation always is.
Yeah.
Yes, the same ones. Whatever cancels in the equations will cancel in the expressions over here.
Yep. So this is to say, as long as you have a matched set, they're conjugate acid-base pairs, this is going to be the case. So your Ka times your Kb is equal to, these two quantities, which you told me what's going to cancel out are your HB and your B minuses, which is equal to that, which is equal to Kw. So on the previous slide, I said that as long as they're conjugates of each other, you take the Ka for the conjugate acid, Kb for the conjugate base, multiply them together, you're going to get Kw. There's the proof. Proof is in the pudding. I wonder where that came from. So we've seen other things where you multiply them together and they equal, because Kw is a constant. So that means they have an inverse relationship with each other. So as Ka goes up, Kb needs to go down. And remember, a high Ka means it's the stronger. The larger the Ka, the stronger the acid. Okay? If you have a small Ka, that must mean your Kb is high for the pair, the conjugate acid-base pair. And I can't remember if it's later I say this, but the problem that we all face, not just you students, but anybody who's in the business of looking at Ka and Kbs, is you're only going to see one or the other. So, for instance, ammonia, NH3, as it turns out, is a stronger weak base than it is NH4 plus is a weak acid. So you're going to see a Kb for NH3, but you won't see a Ka for NH4 plus. So you have to do this to knock out the one that's missing. So this can be helpful, and I think I say that in so many words. But okay, so we've seen this before, but now if we look kind of horizontally, we can pick any. So for instance, if I go across, see how that works? They differ by a proton. Those are conjugate acid-base pairs. Go down here to, they're just all strong. We're somewhere else strong. For chloric acid. Okay, they differ by a proton. This one, acetic acid, I think we dealt with that recently. Remember that we had the problem in the previous part. We had the acetate ion, and on the other side, the product side, we had acetic acid, conjugate acid base pair. The thing about it, I'll just do it. Okay. So let's work a problem. Oh, and this this problem is about conjugate acid-base pairs, but it's also kind of about what we've been talking about. So you might run into a problem like this, where we have a bunch of things, and you see them already listed, And we have to sort through them and say which one is going to be, let's see, arrange them in order of increasing pH. So the lower the pH, the more acidic. So we're going to go from most acidic to least acidic, probably even basic. What I would do, and you can see on the next slide, is to try to pick apart. I'm going to use the WB, the SB, the WA, and the SA to kind of say what we've got going on here. So, for instance, ammonia. I'm going to put a WB there. Does that make sense? It's a weak base. And then when I look at everything, you kind of see I already have blinders on here. When we look at everything, you're going to be able to say, oh, well, I bet that's in my list going to be on the other side of neutral, right? Ooh, ammonium nitrate. Now, a salt, it's an ionic substance. We have a cation and an anion. We're going to dissolve it in water, and we're going to assume that it's entirely going to split apart entirely ionize. So if ammonium nitrate ionizes, we're going to have these running around, and we're going to have these running around. We're going to have ammonium running around and nitrate running around. This will become more likely or make more sense later, but I'm going to put an X through my NO3 minus. Things that are anions like that, you'd be like, well, an anion like that can pick up an H+, so it can be a proton acceptor. So HNO3 accepting a proton. The reason, and the more you do these, the more it'll be like, oh, that makes sense. If it wants to accept a proton, it's going to have to form HNO3. Granted, if it accepts a proton, it's going to make the solution basic. But I'm here to tell you that won't happen. The reason that won't happen is I'm going to put an SA over HNO3. What does SA stand for? Strong acid. It's not happening. It's like going up a hill without any juice. Okay. The other one, though, NH4 plus, I could see it kicking off a proton. If it kicked off a proton, does that look familiar to me? And the answer is yes. And I'm not going to do a one-way arrow. I'm actually going to do a two-way arrow. Because in that sense, it's going to behave as a proton donor, so it's going to behave as a weak acid. That makes sense from left to right. And actually, that's what's going to possibly happen. But it's not any weak acid. I'm going to go ahead and say it's a wimpier weak acid than usual. What I usually say, it's a weak acid of conjugate weak acid. Oh, I can say, well, I was going to say it's the conjugate of a weak base. Yeah, I guess I do that. Weak acid. To be as descriptive as possible, so I go back and I'm like, well, that makes sense. It's a weak acid, proton donor. But honestly, more importantly, it is the conjugate of something that is even a stronger, weaker base. Stronger, weak base. So I'm going to put WA conjugate CONJ of weak base. Cool. See what our other choices are. Formic acid. Now here's where I could ask a leading question, but I'm just going to answer it. Formic acid is not listed in your strong acids. So formic acid, you should be kind of thinking chemical equilibrium. Formic acid, HCOOH. And the reason we write this is to show this guy kicking off is going to be in equilibrium with HCOO negative plus H plus. Okay? So before the test that you have in a few weeks, memorize the strong ones. Okay, so I'm going to put WA, weak acid. Nitric acid. SA for strong acid. What else we got? Sodium formate is kind of like the ammonium nitrate. in that you think, I cannot picture how sodium could be acidic or basic. Sodium is along for the ride. Sodium is not going to do anything. We'll put an X through it. It's a spectator, kind of like nitrate, and it's not going to do anything. But can you see where that, and anions are notorious for them being proton acceptors. Can you see where this guy can accept a proton, basically like I showed up here, right? Basically, no pun intended. So anything that can accept a proton, grab a proton from a neutral Y molecule, minding its own business, is going to create the hydroxide ion. Okay, oh, that's not right. Proton, sorry, that won't work. I have to do new equilibrium, don't I? Here I go. Here's the formate ion, CH3COO-, water molecule minding its own business. In chemical equilibrium, it forms your HCOOH. That's your formate plus OH-. So what I'm going to do is I'm going to put a WB weak base, but it's a wimpy weak base. Weak base, it is the conjugate of a weak acid. What else we got? Oh, all right then. So do you guys buy this? See where I put my X's? Nitrate, spectator. Sodium, spectator. Sodium nitrate, spectator, spectator. That thing's going to be neutral. There's nothing in there to change the chemistry, or the pH anyway. Potassium hydroxide. So can you see where, and who was it? Somebody in here you guys talking to. The hydroxides of anything that with a metal from 1A or 2A are just going to ionize entirely. So I'm just going to draw an arrow up here and show you this thing splitting apart to give you K pluses and OH minuses. And we know that OH minus is a wonderful proton acceptor. So basically, your OH minus is going to be the fact it creates a mole of OH minus means it's a strong base. So I'll put SB there. All right, I guess I should put here. So that's it. All right, so now from the most acidic to the least acidic, my most acidic is going to be my strong acid, followed by my weak acid, followed by my weak acid of conjugate base. Sorry, weak acid of, what did I say? Weak acid, it's a conjugate of a weak base. And then I'm going to hit neutral. And then I'm going to go wimpy, my wimpy base, which is a weak base. And it's a conjugate of a weak acid. And then I'm going to go weak base. And then I'm going to go strong base. So every semester teaches differently. This is the first semester I've ever done a whole list. Because not that it's all about the test, but it is about what we need to kind of learn in this material. How do these kind of rank? So this is the lowest pH to the highest pH. So with all of that said, we end up with this ranking. So HNO3, most acidic, strong acid. KOH, most basic, so it has the highest pH, strong base. We have two weak acids. We have the stronger weak acid, which is a weak acid. That's the HCOOH. And then we have the weak acid that's a conjugate of a weak base, which was, and if I was writing this, I might just put NH4+, because the NO3- didn't do anything. So this is their NH4 plus. And then we have the thing that didn't do anything at all, sodium nitrate. That would be our neutral. And then we go on to our wimpy base. And our wimpy base, again, Na was just a spectator, but what drove it, what made it basic, was that HCOO with -1. The formate ion. And then we go on to our normal weak base, which was ammonia. Okay, so hopefully that helps. One of the topics, and actually Thursday's lab, you guys will be doing titrations. And did you? No, you didn't do titrations. Yeah, you did titrations. Okay, good. This is a different type of titration, so it'll be similar apparatus. You'll have your burette and everything, but to understand how the titration is progressing, you're going to have a pH probe in there to measure the hydrogen ion concentration. So when you did your acid-base titrations, I guess I'll get away from your acid-base titrations. Well, maybe not. When you did your acid-base titrations, you had an acid and a base, then you had a reaction arrow goes to form out. Remember, but you got a salt and water. Okay. So the deal is will it be favored as written from left to right? And it depends on the products, how they are. A minute ago, I told you that this will not happen. I told you that NO3, the nitrate ion, NO3 -1, will not combine with take a proton from a water molecule and form HNO3. And I said it was going uphill. Okay. And what the previous slide and the few slides I'm going to show you is it will always wants to go downhill towards go from the stronger to the weaker species. So here we go. HCl, SA, NaOH, SB. It wants to go downhill. So that would be a favorite thing as written. I think that might have been what you guys did in Chem 1. We could go ahead and find conjugate acid-base pairs different by a proton. Well, I got HCl differing by a proton from the chloride ion, and I got H2O differing from a proton by the hydroxide ion. We could remove the spectator ion. This slide kind of confuses me a little bit. But if you have the same thing on either side of the reaction arrow, like we have the chloride ion here, the chloride ion here, the sodium ion here, the sodium ion here, we can remove them as spectator ions. That's why you see we're left with H+, OH-, and H2O. The net ionic equation for all acid-base reactions like this, will look like this. They'll all have the same form. And here's my, here's what I drew earlier. Here's my conjugate acid-base pairs. The HCl is a conjugate acid-base pair of the chloride ion. Sorry, this is all one. And then the other one is above it. So SA, strong acid, SP, strong base, weak base for NaCl, I suppose, weak acid for H2O. So it's going downhill. Let's see what we have here. I'll let the thing kind of talk for it. We could break it up into its ions. Your NaOH should be an Na plus and OH minus. Over here on the product side, this actually is sodium acetate, so it's really this acetate ion, CH3CO minus, and the Na plus. Okay. So again, if we remove spectator ions, I'm thinking you can only remove your Na plus. And so if we bring down what didn't get removed, we have our, this is acetic acid right here, hydroxide ion, acetate ion, and water. Try to find our two, you should always have two pairs of conjugate acid-base species. So here differs by a proton, and here we're talking about the hydroxide ion, not the sodium, but the hydroxide ion versus the water molecule differ by a proton. Again, it's going downhill. Weak acid, strong base, weak base, weak acid. We've been talking about ammonia, and this is ammonium chloride, so you know you're going to see this split apart here in a minute. So what splits apart is the HCl, strong acid, and then the other thing that splits apart is ammonium chloride. So we remove our spectator ions. It looks like it's only the chloride ion. We bring down what's left over, NH3, H plus, and NH4. We go to find our conjugate acid-base pairs. So HCl and Cl minus differ by a proton, and NH3 and NH4 plus differ by a proton. We identify what we've got. Looks like a weak base, strong acid, weak base, weak acid. Never going uphill. Never going uphill. Expect to see that on one of your tests. Never going uphill. Let's answer this. Okay, that's all I know. I'm not going on, people. But yeah, in those two parts, they're big parts. So I'll see if I can say, well, now that we've done this, you should be able to do this homework, you know, so it's not like, oh, man, that's terrible. So have good, gloomy, cold, wet, wintry, snowy weekends. It's just not right.